You're listening to the N2K Space Network.
I'm Josh Klein.
And I'm Elise Hugh.
We host a podcast from Accenture called Built for Change.
Every part of every business is being reinvented right now. That means companies are facing brand new pressures to use fast evolving technologies and address shifting consumer expectations.
But with big changes come even bigger opportunities. We've talked with leaders from every corner of the business world to learn how they're harnessing change to totally reinvent their companies.
And how you can do it too.
Subscribe to Built for Change now so you don't miss an episode.
Welcome to T-Minus Deep Space from N2K Networks. I'm Maria Varmazis, host of the T-Minus Space Daily podcast. Deep Space includes extended interviews and bonus content for a deeper look into some of the topics that we cover on our daily program. And our guest this week is Dr. Paul Jaffe from the Naval Research Laboratory. Now, Dr. Jaffe's work is focused on space-based solar power and solar beaming. That has been a hot topic of conversation this week on T-Minus. You can go back and listen to our chat with Andy Atherton from Celestial Solar on the development of solar technology for spacecraft that we had on Wednesday. But here is Dr. Jaffe introducing his work in his own words.
I'm Paul Jaffe. I've been working at the Naval Research Laboratory for several decades as an electronics engineer, and I've been working in the area of solar power satellites and power beaming for about 15 years. And I'm a federal employee speaking on behalf of the Naval Research Laboratory.
Thank you so much for joining me today to speak about something that I am extremely interested in personally, space-based solar power. So, okay. Can you give us the intro for our listeners who may not know, although I have a feeling many of them might? Can you give us the intro first on what the technology is and how it would work?
Absolutely. So we have been powering satellites using solar cells since pretty much the dawn of the space age. Now, it was noticed pretty early on, and actually, if you want to go back to the science fiction roots, back in 1941 when Isaac Asimov published the story Reason in iRobot compilation. It is the idea that we would collect sunlight in space and then send it wirelessly to the ground. Now, you might ask, well, wait a minute, the sunlight hits the ground without a satellite. Why would we want to complicate this process? And the answer is that the sun, of course, doesn't shine at night, and it also doesn't shine a lot of the time during the day if there's clouds or weather or another similar interference thing happening there. So this idea has been looked at for some time. It actually was the subject of a patent in the 1960s, and there was a lot of work that was done in the 60s and 70s during the original energy crisis by the Department of Energy and NASA to look into its feasibility. And obviously, since that time, the technology has changed a lot. I'll just mention that the attractions for space solar are, of course, like ground solar. It's clean. It doesn't require fuel or produce waste in the way that other forms of energy do. Unlike solar on the ground, it is constant because you can have either a satellite or a group of satellites in space that will be in the sun pretty much all the time. Depends a little bit on the orbit. And one of the really compelling things about it that is very different than any other source of energy is you could actually create a global network of satellites to provide this energy. So you could think of this of doing for energy what GPS did for navigation. Now, of course, GPS is, of course, something we take for granted. And it's worth pointing out that the sun is the closest thing we have to an unlimited source of energy in the solar system.
So how would it work? So if we had a single satellite, a network of satellites, and then they're beaming that power down to Earth, I know some people might imagine the ants being fried by a magnifying glass. That's not it. So what would it look like?
Yeah, so this is actually a topic that is still under lots of discussion. And I will say among the folks in the solar power satellite community that I'm a little more architecture agnostic maybe than some are. There are a couple choices to be made. You certainly need to pick what kind of power beaming method you're going to use, and that could be using radio waves, microwaves, or it could also be using optical, maybe a laser or something like that. Some folks have also proposed just using a mirror to reflect the energy from space to the ground to existing solar farms. So there's arguments for and against each of these. So depending on which of those means of moving energy you selected, obviously the satellite would look very different. So historically, a lot of the attention has focused on using solar cells, photovoltaics to collect the energy, and then using microwave transmission because that does have that favorable characteristic of being able to go through the atmosphere and through the clouds and weather to give you kind of a 24/7 sort of resource, whereas some of the other ones have a bit of a challenge with that.
Understood. So that brings me to, so what are you working on specifically? Because I'm sure you have a point of view on what's preferable, and I'd be very curious to learn more.
Yeah, we've tried to take a really diversified approach in exploring this. We have done a number of space experiments. We actually also, your listeners may be interested to know, we did a STEM demonstration on the International Space Station. We had astronaut Jessica Meir demonstrate how wireless power transmission works. And it is something that is easy enough that we have now had, I dare say, thousands of school-age kids make their own what we call lectenas, and it's basically just a Schottky diode and an LED that you twist together, and then you hold it up to your phone or your Wi-Fi hotspot, and you can say, oh, look, wireless power transmission is a thing. And it is pretty convincing, pretty compelling for folks to see it with their own hand. So we did that in space. We had astronaut Jessica Meir do that. So that was kind of a lower budget experiment, if you will. But we also have done demonstrations where we have actually put up a sunlight to microwave conversion module, working towards the possibility of using that architecture. We flew that on the X-37B spaceplane, which is basically like an uncrewed mini shuttle that launches on top of a rocket. So we flew that in space from 2020 to late last year, and we got a lot of great data on that, showing the efficiency, showing how it operates in the space environment, what the temperature performance was like. And we actually have a paper that's about to be published in about a month with the results for that. We did send out some preliminary results in a paper back in 2021 as well, which it's open access. So if your readers want to look it up, it is called Microwave and Millimeter Wave Power Beaming in the IEEE Journal of Microwaves. That's a nice review paper. And then we also have done power beaming in space using lasers. We have launched this year, back in March, to the space station, a modest experiment called SWELL, the Space Wireless Energy Laser Link. And this is, to my knowledge, the first demonstration of laser power beaming in space. And it is modest. It is over a short distance, about 1.5 meters, and it's only a few watts. But we are pretty happy with our end-to-end efficiency, which is on the order of 12%. Well, that may not sound like much. That's including all of the conversion on the transmitter side through the laser, the beam traveling, all the conversion and efficiency on the receiver side. So all in, that's pretty good. That's not too far from the conversion efficiency of internal combustion engine automobile. So we're pretty pleased with that. We've also done some ground-based power beaming demonstrations. One called Scope M, where the M stands for microwave. We did that, actually two of those, one in Blossom Point, Maryland, where we sent 1.6 kilowatts over a distance of 1 kilometer using 10 gigahertz microwaves. And then we did a very similar experiment up in Massachusetts. So, and that also is documented in the paper that I mentioned, and actually a second paper, terrestrial microwave power beaming in the same IEEE Journal of Microwaves. And then we also did do a laser-based power beaming demonstration on the ground. And I should mention all of these demos, Lectena, PRAM, the X-37B project, SWELL, Scope M, Scopo, NRL's YouTube channel has videos for all of these. So anybody who's interested in delving deeper or learning more, definitely encourage them to check out NRL's YouTube channel and look at the videos on each of these projects. Scopo was optical power beaming on the ground, also over a distance of 1 kilometer, about 500 watts. So we're trying to lay the groundwork and really answer a lot of the fundamental technology questions that are needed to be addressed for space solar to be a thing.
We'll be right back.
I'm Josh Klein.
And I'm Elise Hugh.
We host a podcast from Accenture called Built for Change.
Every part of every business is being reinvented right now. That means companies are facing brand new pressures to use fast evolving technologies and address shifting consumer expectations.
But with big changes come even bigger opportunities. We've talked with leaders from every corner of the business world to learn how they're harnessing change to totally reinvent their companies.
And how you can do it too.
Subscribe to Built for Change now so you don't miss an episode.
This episode is brought to you by KPMG. At KPMG, innovation is the go-to state of mind. Their visionary thinkers and advanced technology help you see beyond the now, uncover new insights, and turn them into opportunities. KPMG can help you leverage the value of data and drive transformational outcomes through innovation. To explore their thinking, go to kpmg.us.
I know for people like myself who are really jazzed about the technology and its potential, many of us who read Asimov and were really inspired by his writings especially, I know for some of us, like, the case has been made, but for folks who are skeptical about if this is ever going to be feasible or, like, why do it at all, how do you make that case about why it's important?
Yeah. So if it does work, it is kind of hard to overstate how important it would be. So I want you to imagine, like, a world where one country or one company, like, masters this technology, and now they can basically be like the electrical utility for the world, right? So we have many people around the world whose standards of living are rising. Their per capita energy consumption is going to increase, and that energy is going to have to come from somewhere. And if there's one country or entity that can say, oh, set up this receiver and we'll beam you all the energy you want and we'll charge you for it, if a country is going to do that, I probably would like it to be the United States. So there's a huge geopolitical implication here. There's I think, potential parallels between, if you look at, like, how traditionally liquid hydrocarbons, oil in particular, has been controlled by a small number of countries, that similarly could be the case with energy. I guess the implication here, which sadly many people take for granted, is energy is absolutely fundamental to our society, right? Like, we take it for granted that listening to this podcast, you have something that's powering whatever you're listening to it on, and we're talking here over the web. So energy is pretty fundamental. You need it to just about everything. That makes it very important. In terms of the feasibility, I think it's an open question, and I think it's important to look at, right? Because there's no physics reason you can't do this. And certainly, I think talented engineers can find a way to answer the engineering questions. But the larger question is probably, can it be done affordably, right? And I don't think that's been answered yet. Now, it's true that we have seen in the last 10 years the advent of truly reusable rockets, which will certainly bring the cost of putting this into space at a much lower point than it would have been before. We have also seen the advent of true mass production of spacecraft. So if you're going to build satellites to do this, like, you can't be, like, assembling them, like, piece by piece in, like, a giant clean room with a lot of people, right? It's going to have to be more like a mass-produced sort of affair. So the prospect for the cost to come down, I think, is real, but it might take a while. Like, if you look even at, like, terrestrial solar, it took literally decades for that to get to a point where it was competitive and ultimately surpassed sources like coal and natural gas. So I don't think it is probably prudent to expect that this is going to be cheaper than anything else by, like, next year, because there's still a lot of work to be done.
I would never hold you to that. But yeah, no, it is the feasibility question is a fascinating one. So let's switch gears entirely. So I'm sure you're working on this fascinating technology with a number of other agencies and maybe some commercial companies you're partnering with or you're aware of. Can you maybe walk me through what the landscape looks like right now?
There are a lot of people working on it, and definitely the number of people working on it in just the last few years has increased dramatically. As we speak, there's a IEEE conference in Portugal where there's a whole session just on solar power satellites. And then the month after that in Baku, Azerbaijan, there's going to be another conference where there'll be whole sessions on this. And that's just the folks that go to the conferences, because there are plenty that don't. So obviously NRL has put some time and effort and technology development towards this. There are other folks in the U.S. government that are doing it. The Europeans have done a number of studies and are also putting money into it. The folks in the UK, Japan, South Korea, China, there are many activities going on all around the world. And on the commercial and startup side, you definitely have quite a few companies that are pursuing this with ostensibly the hope of turning it into a profitable business. So there is a lot of activity. As I mentioned, I think there's still a lot of unknowns. Like I said, I personally would not pick like a particular architecture at this moment because I'd like to see a little bit more advancement on the power beaming technology side to get a sense of how the challenges will unfold there. There's a lot of folks working on it, to be sure, and it does have, I think, strategic implications, right? So some folks have compared it to sort of the early days of the communication satellite industry. So you might know that in the 60s, we were launching a couple satellites here and there, and people realized like, oh, we could use these to communicate across the world. And forward-thinking folks in the U.S. Congress introduced the ComSat Act and stood up ComSat and Intelsat and engaged the International Telecommunications Union to kind of set up the regulatory framework that was needed for communication satellites to become a thing. And that has yet to happen for solar power satellites. It could follow that kind of path, or maybe it could follow a path more like GPS. That was an instance where the U.S. government made all the investment, so they started using it, and everybody saw it had a tremendous amount of utility. Other countries realized that they wanted to build their own satellite navigation constellations. You look at Galileo in Europe or GLONASS in the European Union, and other countries around the world have navigation because they see how important it is. So you could see something, it could be developed by a single country, it could be developed by a coalition like the International Space Station or ITER, which is the International Thermonuclear Experimental Reactor, where again, you have an energy project that could transform human civilization. And because of that, you have a lot of folks working together that don't usually work together on a lot of things. So a similar potential, I think, exists for space solar.
It really boggles the mind a little bit to think about how really transformative this technology could be at some point in the future. I'm sure there's a lot that you're working on that's in the pipeline. So anything you can share with us about what's next?
Yeah, so we do have projects in progress. We have not publicly released a lot on those yet. I will mention we have successors to some of our completed projects, and certainly on the power beaming side, the thing that we are trying to do is to increase the distance over which we can send power wirelessly and also the level of power. So those are kind of obvious things to do. In my presentations, I have a log plot that shows in the lower left corner kind of what's been done, and in the upper right corner where we need to get. And it's quite a ways. So it's true that once you launch an electromagnetic wave, it's just going to keep going. But you have to consider things like diffraction and how you do beam collection efficiency and those sort of things. So we're definitely focused on those areas.
This is such a fascinating conversation for me, and I really appreciate you sharing what you're working on and also your expertise. This is an area that I know a lot of us are really excited about, and it's just fascinating to hear what you're working on. So, Dr. Paul Jaffe, thank you so much for sharing your time and expertise with me today.
My pleasure, Maria. Thanks.
That's it for T-Minus Deep Space for September 23rd, 2023. We'd love to know what you think of this podcast. You can email us at space@n2k.com or submit the survey in the show notes. Your feedback ensures we deliver the information that keeps you a step ahead in the rapidly changing space industry. This episode was produced by Alice Carruth, mixing by Elliot Peltzman and Trey Hester, with original music and sound design by Elliot Peltzman. Our executive producer is Brandon Karp. Our chief intelligence officer is Eric Tillman. And I'm Maria Varmazes. Thanks for listening.